Good evening, one and all. I am Dr. Shashi Kempanna, Assistant Professor, Department of Electronics and Communication Engineering, Dayanand Sagar College of Engineering, Bangalore, India. Today, I am going to give a presentation on Revolutionizing Brain Tumor Diagnosis, or ResNet18, and Focal Loss Approach to MRI-based classification in Neuro-Oncology. Next, contents are Introduction, Literature Survey, Objective, Methodology, Results and Discussion, Conclusion and Future Scope. Introduction. In this research work, deep learning techniques with the ResNet18 architecture with the focal loss was used to investigate the brain tumor categorization in neuro-oncology with a particular focus on MRI scans images. Loss curves with the expected L-curve pattern show that model exhibits promising convergence during training. The model effectively distinguished between tumor and non-tumor classes as demonstrated. So in this introduction, accurately identifying and classifying brain tumor using medical imaging techniques is essential in the field of contemporary healthcare. So importance of accurate diagnosis, essential for determining tumor location, type, and treatment, critical in reducing cancer-related mortality and morbidity rates as emphasized by World Health Organization. Role of MRI. MRI provides detailed anatomical data crucial for diagnosing brain pathologies, including tumors. An indispensable tool in neuro-oncology. Advances in medical imaging and AI. Convolutional neural network have significance impacted your medical imaging. CNNs excel in image analysis, pattern recognition, and feature extraction, especially for brain tumor diagnosis. Advantages of convolutional neural networks are handle large data sets with high accuracy and robustness, particularly effective in identifying complex spatial patterns in MRI images. Introduction of residual networks, it's also called ResNets. ResNets address training issues in deep neural networks through skip connections, improved performance and faster convergence during training. Literature survey. So these are some of the literature survey that have been carried out for my work. One is Goswami. From his work, the neural network techniques based on unsupervised learning for MRI classification has been taken. Zwerg with the multiple stage automatic techniques for tumor diagnosis and vasculature assessment. Pedard with the modified unit structure for brain tumor segmentation. Thara with the segmentation using a K-means and Fuzzy C-means clustering. Kavita modified area growing techniques for tumor detection. Sunil 3D MRI scan classification focusing on accuracy and overfitting issues. These are some of the literature surveys that are carried out. Based on these literature surveys, some of the objectives that are set are two objectives, that is, focuses on brain tumor classification using CNN, particularly ResNet architecture, aims to enhance neuro-oncology and improve patient care through precise and automated diagnosis. So based on these objectives, these are the methodologies have been set. So the first one is a dataset overview. So in this dataset overview, MRI dataset divided into two main classes, mainly tumor and non-tumor. Tumor classes further subdivided into glioma and meningioma. Data sizes are 4255 images, 4255 images for training. Tumor classes are 2660 images. No tumor classes are 1595 images. So test sets are 1011 images, that is 405 no tumor and 606 is a tumor. Pre-processing techniques, blurring filter applied to reduce noise and enhance image quality. Purpose, minimize the impact of unimportant artifacts and improve feature extraction by convolutional neural network models. So the control rotation used to diversify and augment the datasets. The purpose of this to expose convolutional neural network models to various orientations and improve generalization. The purpose of pre-processing, improve model robustness and feature extraction capabilities, enable convolutional neural network models to accurately differentiate between tumor and non-tumor entities, optimizes the model's performance for real-world scenario through enhanced generation. So here we can able to see the some of the images that are the first row consists of the image belonging to the tumor class and second row consists of the images belonging to no tumor classes. And the figure 2 you can able to see this L and R, that is the original image, blurred image and controlled rotation of the blurred images. So our approach is ResNet architecture. Here residual learning, the address vanishing gradient problems and speed up training convergence. It focuses on identifying mapping learning residuals, that is difference between desired mapping and a layer output. The shortcut connections are bypasses one or more layers by adding input to output. Second thing, we preserves original information, that is identity, along with the learned residuals. Streamlines training when the optimal transformation is near the identity. The second is ResNet18 architecture. This initial layers are 7x7 convolution layers for downsampling, followed by max pooling layer. Second one is the residual blocks. Here, 4 blocks of residual blocks with a batch normalization, RELU activation, and skip connections. 18 layer in total, essential for extracting complex features. Final layer is a global average pooling for spatial dimensions, followed by fully connected layer with a softmax activation for classification. Next, here we can able to see the ResNet18 architecture. This focal loss was used to rectify the underlying class disparity in this implementation between the tumor and no tumor categories. So here in this situation, when there is a class imbalance, the traditional cross entropy loss function tend to be skipped in the favor of majority class, creating what is known as the class imbalance problem. This problem is addressed by focal loss, which selectively downweight the loss attributed to correctly categorized samples and emphasis difficult to classify the cases. When implementing this ResNet18 for a classification task involving imbalanced classes, focal loss is integrated as the custom loss function during training. This strategic integration ensures that model prioritize learning from the minority classes, thereby improving it discriminates and classification of rare or challenging examples. So loss function, that is focal loss, purpose, modulating factors, focusing parameters. So based on this, these are what are the explanation that are given for the ResNet architecture. These are some of the examples that have been given here. So here coming to this focusing parameter, here adjusted to balance focus between the well-classified and challenging instance. Whereas implementation strategies come to the focal loss integration, replace standard cross entropy loss for imbalanced classes. Prioritize learning from minority classes for improved classification or rare instances. So training details are model trained using ADAM-W optimizer over 25 epochs, whereas goal is to enhance the model's ability to accurately classify MRI images as a tumor or non-tumor. Coming to this focal loss, in this picture, you can able to see this is the proposed ResNet18 with the focal loss model architecture. So here you can able to see the brain MRI data and the ResNet architecture with the focal loss. So based on this, we're going to get the tumor or non-tumor. So when implementing this ResNet18 for classification task involving imbalanced classes, focal loss is integrated as the custom loss function during training. This strategic integration ensures that the model prioritizes learning from the minority class, thereby improving its discriminant and classification of rare or challenge examples. Throughout the training phase, focal loss replaces the standard cross entropy loss function, calculating the loss for each instance in the mini batch and the subsequently averaging to obtain the overall loss. The hyperparameter gamma in the focal loss can be fine-tuned through empirical experimentation to achieve the desired equilibrium between the actuating challenging examples. By incorporating focal loss with the ResNet architecture, the training losses of the model is optimized to effectively handle imbalanced classes. This enhancement enhances the model proficiency in the classifying MRI images. So the model was trained by using the ADAM-W optimizer and minimizing the focal loss functions over a period of 25 epochs. The parameter of the model were iteratively refined over the chosen epochs in order to maximize its performance in correctly categorizing brain MRI images. Improving the model's capacity to discriminate between the tumor and non-tumor classes was the main goal of this training. So coming to the results and discussions. So in these results and discussion, here you can able to see the training and validation performance. So L curve pattern, training accuracy and validation accuracy. So in this figure 5, you can able to see the training and validation curve. The yellow color indicates the validation loss, whereas blue color indicates the training loss. So the training accuracy here achieved is 96.5% and demonstrating the model ability to correctly classify brain MRI images within that training data set. Whereas the validation accuracy the obtained is 92.25% and highlighting strong generalization capability on the untested data. The next, here we can able to see that AUC, that is area under the curve. So here the training under area under the curve and validation area under the curve shows the model learning trajectory over 25 epochs. In this figure, you can able to see increasing the trend signifies improved ability to distinguish between tumor and non-tumor cases. Thirdly, we have the test data performance. From this test data performance, we're going to check what is the test accuracy, sensitivity, and specificity. So from the test accuracy, I can achieve 95.54% of accuracy on this test data of image 1011. Sensitivity, I can get a 96% demonstrating this model. Specificity, I will get 95% specificity, reflecting a strong balance between correct tumor identification and minimizing the positives. Next, here we can able to see the confusion matrix analysis. See, this confusion matrix analysis gives the false negatives, false positives, and clinical implications. So in this figure, you can able to see that no tumor, tumor, and predictable labels. So based on this, the false negatives, that is low count of 26 indicating minimal undetected tumors. In the false positives, low count of 19 showing few incorrect tumor detections. Clinical implications, that is high accuracy and low error rates, validate the model's potential for clinical use in accurate brain tumor classification. The next, impact on clinical applications. Here in the clinical application, that is the discriminatory power, potential for personalized treatment, and model limitations, that is dataset enhancement. So discriminatory power is a high accuracy and specifying make the model valuable for faster and more accurate patient diagnosis. Model's ability to effectively categorize the MRI images could facilitate tailored treatment plans and timely interventions. Model limitations are dataset enhancement, where from this substantial dataset, further enhancement may be needed to improve generalization across diverse patient demographics and image variations. So coming to this conclusion part, so high accuracy, excellent sensitivity and specificity. High accuracy, here the achieved a 96.5% of training accuracy and a 92.25% validation accuracy, demonstrating robust model performance. So in this, the analysis of convolutional neural network model with the ResNet architecture for the purpose of classifying brain tumor from MRI images has encouraged implications. For the fields of neuro-oncology and medical imaging, the model convergence during the training is highlighted by the L curve pattern as shown in the previous figure, that is 4, which is the visual depiction of the loss curves. This convergence indicates that model weight and parameters have been refined iteratively, leading to decreasing losses and demonstrating the model's ability to extract discriminative features from MRI images. The model's significant capacity to discriminate between the tumor and non-tumor classes is demonstrated by the remarkable training accuracy of 96.5% and validation accuracy of 92.25% attained after 25 epochs. The excellent sensitivity and specificity test results showed is 96% and sensitivity by 95% specificity ensuring accurate detection of both tumor and non-tumor cases. Effective uses of focal loss address the class imbalance leading to balanced model performance across both classes. Clinical potential. Model's high precision reliability make it promising for early brain tumor detection and treatment planning in medical imaging and neuro-oncology. Next, coming to the future scope of this, the dataset expansion. So in the dataset expansion, they include more tumor types and stages to enhance model, general and robustness, and multimodal imaging, that is integrate additional imaging modalities, that is CT scans, PET scans for comprehensive diagnostics. Clinical integration, develop a user-friendly clinical decision support system to facilitate adoption in healthcare settings. Clinical trials, conduct prospective clinical trials to validate model performance in real world scenarios. So coming to the next references, these are some of the references I made. Yes, you can just go through those references. These are the references. Thank you one and all. Thank you.